So, oversampling. How can oversampling help, and what are the ways in which we can leverage it, we can take advantage of it. Okay. So, oversampling basically means that we can when you do the representation, the copies of the spectrum now come further apart, right. That's what is the so let us take a simple case that I do 2x oversampling. Now this is where you will start to see the benefits of what we have done, what we have discussed. Okay, so when you have quantization noise, basically it is uniform and over the entire range that we are going to be working with. So anytime you have quantization noise, you have to worry about. So the reason we would go to 2x first and foremost, before, if you want to do sampling, would be to do anti-aliasing filtering. So you need to have an anti-aliasing filtering before you do sampling. If I were to do Nyquist sampling, my anti-aliasing filter would have to be of this form. Anti-aliasing filter would have to be of this form, correct. Once I have this sort of an anti-aliasing filtering, then the quantization, then I will quantize. But the problem is, if I do this, then my next copy of the spectrum comes right there. I do not have any room to do manipulation on the quantization noise. I am stuck with the quantization, and also the fact that I am going to have a very restrictive design of the anti-aliasing filter. Now if I say that, okay, I am going to allow 2x oversampling, that means these are not in the picture. This is not there, this is not there, this is not there, this is the 2x oversampling. I now have separated it out. Now so the anti-aliasing filter does not have to be as stringent as before. It could be something that has got a representation, as you know, we have designed these filters. You want to keep only the desired portion of the signal spectrum. So keep it flat in this portion and then have a drop off. Okay. Now what will this do for the quantization noise? Quantization noise is going to be present across, right. So basically quantization noise will get generated across. So effectively what you will see with after the signal is present is that you will see the signal is present here, there is some effect of quantization noise. So the effect of the quantization noise is that there is quantization noise in the desired signal band, right, and of course outside of it also because the anti-aliasing filter did not kill all those samples, there is the quantization noise, but basically you will see some kind of a roll off of the quantization noise. Okay, so there is the noise is present even outside of the signal spectrum. Okay, now so this goes and now if I downsample by a factor of 2, which is what you would need to do to achieve, I have oversampled it so after the anti-aliasing filtering, so oversample by a factor of 2, I have to at some point downsample by a factor of 2. So which means that I would now apply a digital filter and then downsample by a factor of 2. This would be a digital filter. And this, by the way, is an analog anti-aliasing filter. Analog anti-aliasing filter. Okay. Wait. The desired signal is that's a good question. The desired signal plus some unwanted signal is not necessarily quantization noise, you are correct. I have to be careful with this. So what has been allowed by the that I am very correct. Okay. What has been allowed by the anti-aliasing filter is some portion of the signal that is outside. Okay, I do not know what is outside. I have my desired signal. There could be something beyond my desired signal outside the bandwidth, and it is that portion of it. So it should not be orange. It should be something else which is part of the continuous time signal that is present there. after quantization noise will go all the way from up to the sampling frequency. I have to down sample and then get rid of the, you are right. So this is actually not orange, it is actually red. The quantization signal has to be flat. Okay, quantization comes after the anti-aliasing filtering. This portion is what has come in. I do not know what is outside of my signal band. It may be the adjacent channel, it could be some other unwanted signal. So some other extraneous signal that is present, which has come into my system because my anti-aliasing filter is not very tight. Okay, but subsequently I will get rid of it. Okay. So this is a way which we originally said when we were talking only about sampling, we did not talk about quantization. We said that this was a technique to actually reduce the complexity of the anti-aliasing filter, if you recall, right. That so we really did not. So, but does this give any benefit at all in terms of the quantization noise, and if so, what is the benefit and how do we quantify the benefit? Okay. So here is the block diagram, and let us take it in a systematic manner. So I have a analog signal x a of t, which is followed by a C to D converter, and this is a oversampled approach. The sampling period, if you were to sort of relate it to, so let me just write it down here. The sampling period must be at least 2 times omega n, where omega n is the Nyquist frequency, the maximum possible frequency. The sampling period is equal to 1 over fs, which is fs is equal to sigma s by 2 pi. So this becomes 2 pi by omega s, this is nothing but 2 pi by 2 omega n. So this would be pi by omega n. Okay. So Ts if you want to do Nyquist sampling would be pi by omega n. So this has been set to pi divided by omega n into 1 over m. That means your sampling period is 1 over m of the Nyquist sampling period, okay, which means that you are oversampling by a factor of m. So this produces for us the signal x of n, which would be passed through the quantizer that would produce for us the x of n plus E of n, the noisy signal plus the error signal, after which we will go into the digital domain, where I will pass this through a low pass filter with cutoff omega c equal to pi over m. The reason we are doing that is because we are going to do a downsampling by a factor of m to take care of the oversampling factor, followed by a downsampling by a factor of m, and here comes the final signal, which is the quantized signal. Okay. Now I will be with you in a minute. So just for differentiating this quantized signal from the earlier type where we did not do any oversampling, just want to write it with the following subscript d. That means it has come through a process of oversampling and down conversion, and x d of n can be related to x d a of n, that is the discrete time signal through this downsampling process, plus x d e of n, that is the error signal. So one is the signal component, this is the signal component, and this is the error component, quantization error component. Okay. So just some notation so that we can do, yeah, there was a question. Yeah.
What is omega n over here? Is it the Nyquist rate or is it the maximum?
Okay, good question. Let us clarify that. This would be in the continuous time. If we were to, now this is all discrete time here. So if you were to draw it, write it in the continuous time, this signal, this is omega n. Okay, and maybe the confusion is coming because of this. Okay, whatever this value is, let us call it omega naught, that is probably the best. Okay. Omega naught minus omega naught, the Nyquist frequency is equal to 2 times omega naught, right. So, and is that what we called as omega n previously? Okay. So, if we have called that as omega n, then just make this as omega naught, make this as omega naught. Whatever is the highest frequency component, it would have to be, so let us change it everywhere. So, this would have to be omega 2 times omega naught for the Nyquist rate. Okay, let us not introduce omega n if we have not introduced it before, and so this would be pi over omega naught times 1 over m. Whatever is the, so pi over omega naught would represent the Nyquist sampling rate, Nyquist sampling rate. Okay, so this is Nyquist sampling rate. Okay. Okay, so given this form, the signal to quantization noise ratio. Okay, so please note what are the, so the signal to quantization noise ratio now becomes SQNR is expected value of x dA of n whole squared. Okay, that is signal power divided by expected value of x dE squared of n. So, that is the signal component, this is the signal part, this is the quantization error part. Okay. Quantization error. Okay. So, here is where I would need you to visualize the process as follows. So, the pictorial representation of this is the following. I have my desired signal, I am going to plot from minus pi to pi, and I am assuming that the reason is you are constrained to only a part of your of the range minus pi to pi is because of the oversampling part. Okay. Now, this has gone through a quantizer of b plus 1 bits. So, the quantization error is uniform in this region. Okay. Now, what does the digital anti-aliasing filter do? It is going to ideally portion of this. Okay. Did the anti-aliasing filter, combination of the anti-aliasing filter in the analog domain and the anti-aliasing filter in the digital domain, did it do anything to your signal? Your signal went through without any issue, right, and no problem at all. So, basically we are leveraging a key concept in the modeling of quantization noise, which is as follows: x of n added with E of n is what produces x hat of n. So, we have modeled the quantization as a linear perturbation, right, basically it is a linear, some other signal that got added. So, when you now think of it in terms of the filtering that it has gone through, you find that there has been no, it is yes x of n and E of n got added, but when you pass it through a linear filter, the linearity does it is the same as passing the x of n through the filter, then adding it to E of n passing through the filter, the property of linearity. So, effectively nothing, no impact on signal. Okay. So, a qualitative statement, okay, no impact on signal, no impact on signal. Okay. So, signal power has gone through untouched. So, whatever was the original signal power, that is what it should do. What about noise power? Reduced or did not make a difference? Look at the spectrum. How much of the noise power is outside of the band of interest? So, in other words, if you have basically retained 1 over m of the total noise power. Okay. So, you have actually, though in the context of the previous time when we discussed oversampling, it was only to reduce the complexity of the anti-aliasing filter, the analog anti-aliasing filter, but now you see that it is actually more than what you actually obtained. You actually now can go through and show the following result. So, basically this is the expected value of x dE of n squared will be 1 over 2 pi integral minus pi to pi, the range is sigma e squared, and sigma e squared, wait a minute, it is actually minus pi over m to pi over m, that is the part that is retained. So, d omega. Okay. So, basically this should come out to, if you go through the process, this should come out to be delta squared by 12 times m, 1 over m times the sigma e squared. Okay. So, this is a huge advantage, because now your signal to quantization noise ratio, the formula is slightly different. Okay, the formula is different. So, let us quickly capture that and then and take it forward. So, the SQNR, signal to quantization noise ratio, is basically sigma squared of x dA, that is the signal part, divided by sigma squared of x dE, that is the signal power by the quantization noise power. So, this is effectively signal power divided by quantization noise power. Okay. So, one step away from a very important result. So, this comes out to be sigma x dA squared, I leave that as is, divided by delta squared by 12 m. So, if you go back and write it in dB, this is in dB, this will be 6.02 B, the same one that we got, plus 10.8 minus 20 logarithm of x of m by sigma x dA times 10 log base 10 log 10 of m, not log base 2. That factor of m has now entered the part. Okay. So, by increasing your oversampling rate, you not only reduce the complexity of the anti-aliasing filter, you actually also benefited in terms of the noise. Okay. So, here is a very important element. We have a thumb rule. The thumb rule says, thumb rule has, from before we know it is 6.02 dB or 6 dB per bit, right, 6.02 dB per bit. Now, if you go ahead and look at 10 log 10 4, basically if you have an oversampling factor of 4, what will you get? Around 6 dB. 6 dB. So, which means that what I can achieve with 1 additional dB, I can achieve with oversampling by a factor of 4. So, of course, if you already have a 16-bit quantizer and you now say I want 18 bits of precision, it is possible, because you can do your oversampling by a factor of 8, and then you will 4 times 4 16, factor of 16, and you will get the required this thing. So, we can also write the following, which is m equal to 4 implies the SQNR will improve by 6 dB, improves by 6 dB, or it is the same as saying that m equal to 2 is equivalent to a half bit improvement in SQNR. Okay, so, you can use that as a relationship and you can work out the key results. Okay. Here comes the most interesting part of this. So, okay, this is good enough, we have done, we actually achieved, but keep in mind that if you want to go from 8 bit precision, let us say you have an 8 bit quantizer and you want to get 16 bits of equivalent performance, you will find that m will become very large. So, you will have to have a lot of complexity. So, here is where the thought process comes in, and we look at this figure, and the question that raises, Does the quantization error need to be spectrally flat? Does the quantization error need to be spectrally flat? Answer is, the way we do quantization today, it is going to be that way, there is nothing we can do about it. So, we then ask so this is spectrally white. What are we asking? Can we make the spectral, the quantization noise colored? Coloration of the noise. Coloration depends on some kind of memory between adjacent samples. Only when you have memory you can introduce coloration. So, basically if each of these samples are independent of each other, we cannot produce that. So, the question is, can you do something in terms of the coloration? And here is the simplest of the structures that introduces coloration, and let me sketch it for you, leave it for you to do a little bit of analysis. We will pick it up from here, and then in the first part of tomorrow's lecture we will conclude this discussion. So, here is a modified quantizer. I have the analog signal XA of t. This is going to be the C to D type of quantizer. So, I am going to precede the quantizer. So, basically we will think of it as, instead of C to D, as an A to D converter. So, basically it is a finite number of bits conversion apart, but I am going to precede it with a integrator. Okay, I am going to precede it with an integrator. So, what is an integrator? An integrator is one that adds all of the past samples, right. So, can you write for me the impulse response of a integrator? Hi of n is equal to 1 for all values of n, starting from n greater than or equal to 0, right. So, basically that is a causal integrator. So, if I were to ask you the filter response of this Hi of z, Hi of z integrator Hi of z is 1 plus z inverse plus z minus 2 dot dot dot, this is 1 over 1 minus z inverse. Is it stable? No, it has got a pole on the unit circle. So, it is not a stable system. So, a discrete time integrator is not a stable system. However, if you were to control the stability part, so think of this as a 1 over 1 minus z inverse. Okay. If you need to cancel out the effect of the integrator, you must differentiate first. So, how do I differentiate first? So, I take this signal and subtract it from the difference. So, basically with a minus sign, with a minus 1. Okay. So, if I oversample my signal, two successive samples will look almost the same, right. So, if I subtract out the previous sample, it looks like I am making a differentiation of a small step differentiation, x of n minus x of n minus 1. Then I pass that through an integrator and then quantize it. Now, you may say, well, really does this make any difference? You differentiate it and then you are cancelling it. So, look at the following aspect. So, if that is 1 over z inverse, think of this as a z inverse, treat this as a point where the error signal comes in. Okay. So, the equivalent diagram that I want you to look at is the following: XA of t followed by a C to D, which is a perfect quantizer, no quantization error, and then an additions part. So, this is a discrete time equivalent of what we have drawn there. The integrator is 1 over z inverse followed by the quantizer. I am going to draw it as the addition of the, so this is the quantizer, I am going to add it and show it in terms of the addition of the error signal. I am going to take this input with a delay and subtract it from my output. Okay. So, this is the output signal which I want to analyze, and so we would now look at have we done anything to the what we would like to show is that the signal goes through. So basically what I want you to do is if the output signal is x d of n, if this is x d of n, think of it as two inputs, one is the signal, the other one is the error. I want to look at the transfer function for the signal part and the error part, and then we will take it forward from there. But the key thing to note is that this is an attempt to color the noise, and the coloration of the noise basically says I want to do something. If I cannot do anything to the energy of the noise, the total power will remain the same. So if I can do something like this, redistribute the noise in the quantization, then what I can do is actually when I do the digital filtering, I can throw out more than what I could do before. So that half bit improvement can now become 1 bit improvement, 2 bit improvement, 3 bit improvement, depends on how you have shaped the noise. Okay. So that is what I will just show you the noise shaping part, but basically it is a very interesting mechanism where you start thinking, saying I do not want flat, which I must introduce some sort of memory between the successive samples. How do I do that? That is what we are going to be looking at tomorrow. Okay. And all this is possible because you have the flexibility of the sampling rate. Okay. Thank you very much.